Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 5. Use of non-uniform grids. Non-uniform grids are used in the numerical solution of two-point boundary value problems to improve accuracy, efficiency, or adapt to specific characteristics of the problem being solved. Non-uniform grids offer significant advantages in the numerical solution of ordinary differential equations, especially for problems with varying solution characteristics, such as boundary layers or singularities. In this regard, non-uniform grids can provide higher accuracy where it is needed and coarser grids elsewhere. Non-uniform grids introduce complexities in implementation and require careful handling of stability conditions and the adjustment of numerical schemes. A suitably designed grid results in good quality numerical estimates. Conversely, a poorly constructed grid yields poor numerical estimates. In many instances, the difficulties with numerical solutions may be attributed to poorly constructed grids. Thus, the gridding step that should not be underestimated to obtain quality solutions. Using a uniform grid does not always give satisfactory estimates for cases with boundary layers unless fine grid spacings are used. The purpose of using non-uniform grids is to increase the grid density near the boundaries, where sharp changes are expected. In this way, the CPU time can be seriously reduced by adopting non-uniform grids, leading to smaller linear systems. Grid generation in the one-dimensional case is a simple task in that the nodes are concentrated at one or both ends of the solution interval or at an arbitrary interior point. There are many techniques for grid generation, covering a considerable portion of computational work. Generating arbitrary grids can be done manually by the user or, generally, using a grid generation algorithm. For instance, stretched grids can be obtained by specifying the first interval size, h, and a growth factor, r. This avenue of specifying non-uniform grids increases the computational burden. In this illustration, the grid points spaced apart with distances that grow according to a geometric series for a greater than 1. For r less than 1, the grid points spaced apart with distances that decrease according to a geometric series, leading to nodes concentrated at the right side. On the other hand, when grid points are non-uniform, standard difference formulas do not apply. Approximating first and second derivatives is more complicated because of different adjacent step sizes. This can also lead to a loss of accuracy or incorrect derivative approximations. Solving the ordinary differential equation numerically can become more complex without transforming the problem to another space. An alternative technique requires the coordinate transformation of the physical domain in X space into a computational domain, C space, to which uniform grids can be applied. An ordinary differential equation is first transformed from X space to an equivalent ordinary differential equation in C space. Then, the transformed ordinary differential equation is solved with uniform grids. A grid stretching function x equals xc dictates the nodal distribution in X space. For instance, a simple stretching function involving power functions such as x equals a plus b minus a times xc to the n, where xc ranges from 0 to 1, may be used to construct non-uniform grids on the interval from a to b. The effect of stretching functions in power form are illustrated here. Nodes are clustered near the right boundary for n less than 1. Nodes are clustered near the left boundary for n greater than 1. Consider transforming the following two-point linear boundary value problem into a boundary value problem in Xi space using the grid stretching function x equals a plus c times Xi to the n. The first and second derivatives are transformed to the ones in Xi space using the chain rule as follows. Similarly, the boundary conditions are also transformed to Xi space. Substituting into the original ordinary differential equation gives, where the overlined symbols denote the modified or transformed coefficients. The advantages of the non-uniform grids are numerical treatment of a boundary value problem using a suitable grid stretching function can lead to very satisfactory estimates. It provides improved accuracy in critical regions. Properly designed non-uniform grids may result in a significant reduction in the number of nodes and the CPU time. The disadvantages of the non-uniform grids are numerical treatment of the original boundary value problem with non-uniform grids may not yield second-order global errors. A boundary value problem in a transformed space can be very complicated. Implementing numerical methods with non-uniform grids is often more complex than using uniform grids. Let us consider the following second-order linear two-point boundary value problem. We are asked to use x squared equals Xi as a stretching function to transform the boundary value problem in X space to a boundary value problem in Xi space, and solve the transformed boundary value problem using the finite difference method with m equals 5 and 10 uniform intervals. Then, we will compare our estimates with the given true solution. The stretching function x squared equals Xi concentrates the nodes on the left boundary, as illustrated below for various m values. This type of gridding would be desirable if the function yx depicts sharp changes near the left boundary. Next, to begin transforming the differential equation, we first find dxi over dx. Differentiating both sides of the transformation equation gives. Applying the chain rule, we find Applying the chain rule again for the second derivative, we get. Substituting the first and second derivatives in Xi space, we obtain. Simplifying gives the final ODE. Next, we turn our attention to the boundary conditions. The right boundary condition is the easiest as it yields the same condition. Y value at x equals 1 is 4 or y at Xi equals 1 is also 4. Since Xi is 1 for x equals 1 due to transformation equation. The left boundary condition needs some work. Recall that we found earlier that dy over dx was equal to dy over dxi times 2x. Let us investigate the derivative dy over dxi in the limit sense at the left boundary. Applying the L'Hopital's rule gives y double prime 0 over 2. To determine the second derivative at x equals 0, we make use of the differential equation. Taking the limit as x goes to 0 results in 8 times the left node value. Finally, substituting this into above limit, we obtain. The transformed two-point linear boundary value problem takes the following form. The numerical solution steps are carried out as usual. However, The difference equation for the left boundary is obtained from the Robin boundary condition using the forward difference formula as follows. Here we discretize the Robin boundary condition using the second-order forward difference formula to avoid creation of a fictitious node. We leave it to you to discover why we took this route. For m equals 5, the system of linear equations in matrix form is obtained as follows. This is not exactly a tridiagonal system due to the first row. However, the forward elimination and back substitutions can be employed in the same manner. Keep in mind that the first row third element must be used in forward elimination step. When we reach the first row during the back substitution, the values of y1 and y2 are available from prior steps. The system solution gives the true solution. For m equals 10 also we will obtain the true solution. Do you wonder why? We will let you figure it out. With this last note, we conclude this session. That is all for now. See you next time with another topic. Bye.